There are three main types of fuselage. In this lesson, we will discuss the construction of aircraft's fuselage, wings, and tailplane. There are three main types of fuselage construction in use. First, there is the truss or framework type, which is generally used for light, non-pressurized aircraft. Then there is monocoque, which is only rarely used. And finally, semi-monocoque, which is in use on most other types of aircraft. The last two types of structure are more generally referred to as stressed skin. The framework or truss consists of light gauge steel tubes welded together to form a space frame of triangular shape to give the most rigid of geometric forms. Each tube carries a specific load, the magnitude of which depends on whether the aircraft is airborne or on the ground. It is a strong, easily constructed, and relatively trouble-free basic structure. The framework is covered by a lightweight aluminium alloy or fabric skin to give an enclosed, aerodynamically efficient load-carrying compartment. Monocoque is a French word meaning single shell. In a monocoque structure, all the loads are taken by the stressed skin, with just light internal frames or formers to give the required shape. Sandwich construction, which is a honeycomb core with a skin of aluminium alloy or composite material such as glass reinforced plastic or carbon fiber reinforced plastic, can be used to provide rigidity and strength. However, even slight damage to the skin can seriously weaken the structure. To be a true monocoque, the structure would have no apertures in it at all. But for practical purposes, they have to be provided for access and maintenance. The apertures need to be reinforced so that the integrity of the structure is maintained. Once the aircraft doors are closed and all the hatches and access panels are fitted, the fuselage is, to all intents and purposes, a monocoque structure. One of the few examples of monocoque fuselage constructions is the Beech Starship. As aircraft became larger and the air loads greater, the pure monocoque structure was found not to be strong enough. Additional structural members, known as stringers or stiffeners, and longerons are added to run lengthwise along the fuselage, joining the frames together. The light alloy skin is then attached to the frames and stringers by riveting or adhesive bonding. Stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress. Longerons are more substantial than stringers and are fitted where extra strength is needed, such as for the seat rails in passenger aircraft. When cutouts are made to stress skin structures, for example to provide access panels, doors or windows, or when repairs are required to damaged areas, reinforcement in the form of doublers or backing plates is required around the cutout. If the skin is machined from solid metal, then that part around the cutouts is left thicker than the rest to provide the required reinforcement. The flight deck windows fitted to pressurized aircraft must withstand both the loads of pressurization and, because birds also use the sky and are not under air traffic control, they must bear the impact loads from possible bird strikes. To do this, they are constructed from toughened glass panels, attached to each side of a clear vinyl interlayer. Windscreens are surrounded with a rubber seal and attached to the frame by bolts passing through the extended edge of the vinyl interlayer. An electrically conductive coating applied to the inside of the outer glass panel is used to heat the window. This prevents ice from forming and maintains the window's flexibility, making it more able to withstand bird strikes. The shock loading of a bird strike impact is absorbed by the ability of the vinyl interlayer to stretch and deform should the impact be sufficient to shatter the outer glass. The aircraft must be capable of continued safe flight and landing after impact with a 4-pound or 2-kilogram bird when the velocity of the aircraft is equal to its design cruise speed, VC, at sea level, or 0.85 VC at 8,000 feet, whichever is the most critical. In other words, the windscreen must be able to withstand this impact without penetration. The vertical and horizontal angles of the windscreen are specified so that each pilot has a sufficiently extensive, clear and undistorted view to be able to safely perform any maneuvers within the operating range of the aircraft. It is important that the pilot has his seat in the correct position to get a good view forwards and downwards out over the window, over the coaming and nose of the aircraft, without restricting his overall view. To help with this, reference eye points are often painted on the flight deck windscreen frame. On some aircraft, an opening window to the side of the windscreen, known as a direct vision or DV window, is provided to enable the pilot to have sufficient visibility to land the aircraft safely should the windscreen become obscured. These windows are also sometimes used as emergency exits. Passenger cabin windows are designed to be fail-safe and normally have 2 panes of acrylic plastic mounted in an airtight rubber seal fitted into a metal window frame. The inner and outer panes are each individually capable of taking the full cabin pressurization load, so if one pane fails, the other will prevent loss of cabin pressure. The wings support the weight of the aircraft in the air, and so must have sufficient strength and stiffness to be able to do this. Their strength and stiffness is determined by the thickness of the wing, with the thickness and type of construction used being dependent on the speed and weight requirements of the aircraft. The types of construction are biplane, braced monoplane, and cantilever monoplane. Very few biplanes fly at more than 200 knots in level flight, so the air loads are low, which means that a truss-type design, which is covered in fabric, is satisfactory. The wing spars, interplane struts, and bracing wires form a lattice girder of great rigidity, which is highly resistant to bending and twisting. Unfortunately, this system also generates a relatively large amount of drag, which accounts for the fact that biplanes fly relatively slowly. In flight, the flying wires hold the wingtips down and support the fuselage. On the ground, tension in the landing wires supports the wings. In the braced monoplane type of design, the wing is connected by a brace to the fuselage or landing gear. In flight, the brace is subject to tensile loads and acts as a tie. On the ground, it is under compression and acts as a strut. To provide fail-safe protection, the brace is often made from more than one member. The Shorts Skyvan, for instance, has 3 members per brace. This type of design is mainly used on low-speed aircraft. Now we will look at cantilever wings, the design used by most modern airliners. The wings have to absorb the stresses due to the lift and drag in flight, and, if of this design, their weight when on the ground. This is achieved by building the wing around one or more main load-bearing members known as spars. The wing spars pass from wingtip to wingtip either as single structures or as connected sections. The spar will normally be an I-beam either manufactured as a single part or made up of 2 or more parts to give it fail-safe characteristics. These are constructed so that they will absorb the downward bending stresses when on the ground and the upwards, rearwards and twisting stresses when in flight. In flight, bending stress relief is provided by mounting engines on the wing and by locating the major fuel tanks in the wing. Fuel usage procedures are designed so that the wing tank fuel is used last. This is of particular importance at high all-up weights, when the outer wing fuel tanks should be full. As fuel is used, the weight of the aircraft decreases, which reduces lift required and therefore the wing bending moment. The wing may be of a single spar, twin or multi-spar construction. A conventional structure would consist of front and rear spars, stringers, and ribs, with the metal skin attached to them to form a torsion box. The torsion box functions as a beam, but is considerably lighter than a solid beam of the same size, without losing much strength. The stressed skin takes the loads due to the differences in air pressure and the mass and inertia of the fuel in the wing tanks. It generates direct stresses in a spanwise direction as a response to bending moments, and it also reacts against twisting forces. Stringers are spanwise members which give the wing rigidity by stiffening the skin in compression. In most modern aircraft, they are formed by machining integral ridges into the skin. Ribs maintain the aerofoil shape of the wing, support the spars, stringers, and skin against buckling, and pass concentrated loads from the engines, landing gear, and control surfaces into the skin and spars. Ribs often have lightning holes cut into them. As well as reducing the weight of the structure, these holes are usually flanged to help stiffen the rib. The major structural components of the wing are generally manufactured from aluminium alloys. With composite material, such as glass-reinforced plastic or carbon-reinforced plastic and honeycomb structures, being used for more lightly loaded structures. Carbon-reinforced plastics are gaining wider acceptance for the manufacture of major structural components, such as the fin and horizontal stabilizer. There are a number of aircraft mass limitations that you must become familiar with. The maximum zero fuel mass of an airplane is defined as the maximum permissible mass of an airplane with no usable fuel. This limit is set by the maximum bending load that the wing root is able to support. The maximum zero fuel mass sets the maximum load that can be carried in the fuselage. Fuel added to the wing will not increase the wing bending load. In fact, it will reduce it. Maximum structural takeoff mass is the maximum permissible total airplane mass at the start of the takeoff run. Maximum structural taxi mass is the maximum mass of the airplane at the commencement of taxi. This is sometimes also referred to as the maximum ramp mass. Maximum structural landing mass is the maximum permissible total airplane mass on landing in normal circumstances. The tail unit, which is sometimes called the empennage, comes in many different designs. It can be conventional, T-tail, H-tail, or V-tail. The tail unit provides, in most cases, the longitudinal and directional stability and control. A small number of aircraft have their longitudinal stability and control provided by foreplanes or canards, as seen here on the Rutten Cozy. The horizontal surfaces, which are known as the tailplane or horizontal stabilizer, provide longitudinal stability by generating upwards or downwards forces as required. Longitudinal control is provided by either the elevators or the moving tailplane, depending on design. For instance, the Boeing 747 uses elevators for control and the tailplane for pitch trim, whilst on the TriStar the roles are reversed, the tailplane being used for control and the elevators for trimming. The vertical surfaces, the vertical stabilizer or fin, generate sideways forces as required to provide stability about the normal axis. Directional control is provided by the rudder. The operation of these flying controls is fully covered in the Flight Controls series of lessons. Both the tailplane and the fin are subject to similar but smaller bending and torsional stresses as the wing. Structurally, the tail unit components are generally smaller versions of the wings in that they use spars, ribs, stringers, and skin in their construction. On some aircraft, they may also contain sealed compartments for fuel storage. They are also constructed of the same basic materials as the wings. Usually, aluminium alloys are used, with composites filled with honeycomb structures or high-density expanding foam sometimes being used for control surfaces to provide greater stiffness at low weight. Aerodynamic flutter is the rapid and uncontrolled oscillation of a flight control, or the surface to which it's attached, which occurs as a result of an unbalanced surface. A full aerodynamic explanation can be found in the Principles of Flight series of lessons. Flutter is caused by the interaction of aerodynamic torsion and bending forces, inertial forces, and the elastic properties of the surface or structure. It can lead to catastrophic failure of the structure. Flutter must not occur within the normal flight operating envelope of the aircraft. Flutter can be prevented by mass balancing control surfaces to alter the moment of inertia of the surface and therefore the period of vibration. This can be achieved by positioning balance weights forward of the control surface hinge line to move the control surface center of gravity closer to the hinge line. Flutter of the wings can be prevented by using the engines as mass balance. This is done by mounting them on pylons forward of the wing leading edge. The fact that an aircraft is poorly maintained, particularly in respect to excessive control surface backlash or flexibility, may mean that flutter will occur at speeds below the limit airspeed. This is the end of the lesson. You should now understand the differences between truss, monocoque, and semi-monocoque fuselage construction, and the differences between biplane, braced monoplane, and cantilever monoplane wing constructions. You should also note the following key points from this lesson. Spars on non-stressed skin wings absorb the downward bending stresses when on the ground, and the upwards, rearwards, and twisting stresses when in flight. On stressed skin wings, they are assisted in this by the skin itself. On larger aircraft, a wing torsion box is often formed from spars, skin, stringers, and ribs. Fuselage stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress. Flutter can be prevented by mass balancing control surfaces. Finally, you should know the meaning of the various maximum structural masses to which an aeroplane is limited. Remember that the maximum zero fuel mass of an aircraft limits the bending moment at the wing root, while allowing the maximum load to be carried.